Okay, another show of hands. Can those of you who are on Zoom now see my desktop, my screenshot? Perfect, okay. You can all lower your hands again. Okay, so some housekeeping before we get started. First off, can you all now access the textbook? Were you able to go through the link and establish an account? And now you can read the textbook. Can you read more than just the assigned readings? Okay, good. Second thing, the TA situation turns out is still fluid. We got an email this morning indicating that the TA assignments are still preliminary, so still no, nothing that, yes. So still not sure about the TAs, but of course we don't have homework due yet, so it's not really a big deal until that's the situation. Have started my office hours, so they'll be from 4:15 to 5:15 today if you need to talk to me. One thing I forgot to mention last time, there's not just a penalty for late submission, there's a bonus for early submissions in this course. So if you submit your homework more than 24 hours in advance, you get 5% added to your homework grade. So that's an inducement to you to get your homework done early. And also it helps me because sometimes if there's a bug in the homework assignment, because people get started on it early, I hear about it and can get it fixed. So that's a way for you to earn extra credit in this course. When I get questions about how can I get extra credit, hand in your assignments 24 hours early. They'll get you 5% every time. Okay, 5 points. So, so that I think takes care. We covered the book, we covered the TAs, and we covered early submissions. So that takes care of housekeeping. Any questions about that or from the Zoom folks? Okay, so let's hit today's lecture. So I got a request to make the slides bigger. The best I'm going to be able to do is to go into slide presentation mode. So hopefully, now for those of you who are on Zoom at home, right now all I can see is my PowerPoint presentation. So can someone let me know, can you see this? What are you seeing? Are you just seeing, are you seeing my screen where you see notes and a set of slides at the bottom and then one main window to the left, or are you just seeing one big window?
One big window, PowerPoint slides, just the presentation.
Perfect. Okay.
And it looks much better. Thank you for doing that.
You are welcome. Okay. So today we get going with the relational model, and what we're talking about today forms the basis of the data definition language for the database. So it provides a formal description of the structure of a database. So the relational model, the chapter in the book 16 is covering what forms the basis for the data definition language. Now, on another lecture in a few weeks, we'll talk about the theoretical basis for the query language, which is the relational algebra and calculus. And the book talked briefly about the set of operations provided by the query language portion, things like select, project, join. That's part of the data manipulation language. It's not part of the what we call data definition language. So to be really clear, because it's in the quiz, what we're talking about today forms the theoretical basis for the data definition language. And in 2 to 3 weeks, when we talk about the relational algebra and the relational calculus, at that time, we will be talking about the theoretical basis for the data manipulation language. But to get started, we have to be able to talk about what is a relational database. Okay, what are the rules? So that's what we'll be talking about today. And before I go further, so what we have basically is that a relational database is a set of tables with a set of columns. And what I'm going to do is actually go to Canvas, and throughout the semester, you see this under course materials, you'll see figure 4.3 PDF. And you may want to go to it to yourself if it's a little small, because obviously it's not as big as I might like. There's unfortunately a limit to how big I can make it. But you can feel free to do it on your computer. At any rate, this figure gives you the set of tables that we will be using throughout this course for the examples and lecture. Okay, it comes from a property management example, and it shows you the basic idea. Actually, probably, well, this shows you the data, it's pretty small, so I'm going to head back to the PowerPoint. It might be a little, yep, I think easier to see it that way. Okay, so the essence of the relational model is you have a set of tables, and these tables are called relations. And in the relations, what you have, each table has a set of columns, and they're named. And these are attributes. So in this case, we have a branch, and it has a branch number, a street address, a city where the branch resides, and a postal code. For those of you, we used to use a textbook in this course written by an Irish author, and that's why you see British cities and British postal codes rather than US zip codes, but same idea. And then down here, we have a second table, staff. Again, staff number, first name, last name, position, sex, date of birth, salary, branch number. So this already illustrates a lot of what we're interested in. So generally, a relation is going to be associated with an entity. And these are physical things like a branch office or a staff member. Now we'll get into some other things that relations can be, but one of the most easiest things to understand is that they represent some kind of physical thing. Okay, and these things have properties associated with them that we call attributes. And then we talk about the cardinality of a relation, which is the number of rows. And if we're being theoretical about it and talking about it mathematically, a row is a tuple. But generally, we'll talk about rows because that's generally the more popular vernacular. And then the number of properties or columns that a relation had is called the degree of the relation. So that's the number of attributes the relation has. Then you see up here primary key. The primary key is a column or set of columns that uniquely identify each row in the table. So in this case, the branch number uniquely identifies each row in the table, and down here a staff number uniquely identifies each row. Now these are what are called, and we'll get to it shortly, these are artificial attributes. They are generated, say, from a random number generator to uniquely identify them. Oftentimes, there will be other columns or sets of columns that might uniquely identify things. So quite possible that a first and last name down here in staff might uniquely identify each row in the staff table, in which case first and last name as a pair would be a primary key. Now, as we all know, that's not particularly reliable because there are certainly, John White is not a particularly uncommon name. It's quite possible that we have multiple John Whites. So that is reason that we end up generating these artificial keys, is because that can guarantee that we get uniqueness. That's why we all have social security numbers. That gives us uniqueness. You also see this foreign key right here. And you can think of a foreign key much as a pointer that allows us to point into another table to get us information. So in this case, what it's saying is that John White works at branch B5. If we want more information about that branch, we can follow this key up into the branch relation and find out that that branch is at 22 Deer Road in London. By storing a foreign key here, we avoid having to store all the information about the branch right here. So we could, instead of storing this branch number, just duplicate all this information about the branch and add 3 additional columns to the staff relation. But that would have some problems associated with it. Okay. First of all, we would be storing the information in multiple places in the database. We'd be storing it in the staff relation, and we'd be storing it in the branch relation. And if we change the information in one place, like up here, maybe we change the postal code. If we forget to change it down here, then the postal code's out of date. Another problem is it's just duplicated data because, let's see, there's another person at branch B5, there's 3 people at branch B3, so if we had those additional 3 columns here, we'd be adding a lot of additional storage to the database, which is also undesirable. So these foreign keys give us a way to, we'll call it later, join 2 relations together in order to get additional information when we need it. So think of a foreign key as a pointer. Okay, in this case, it's not a physical memory address, but it is a, it's going to be a primary key in another relation. Okay. So questions about that? Okay, well, this gives you already a very good idea about what a relational database is. A table with a set of rows, and then each row has a number of columns, and each column has a domain type and that domain type, you can draw the values for that column from that domain type. Okay, so here's just a formalization of what we just said. So these are the mathematical terms. So relation, attribute, domain is an allowable set of values for 1 or more attributes. Okay, a tuple is a row. We talked about degree and cardinality. So a relational database is a collection of normalized relations with distinct relation names. Okay, so you can't have duplicate relation names, which makes sense. And this is the key word here, normalized. What that means is that typically the only shared columns among relations are foreign keys. So going back here, I said we could have added these three columns to the staff relation, but that would have been redundant, okay? So these two relations are in what are called normalized form. The only duplication is in the foreign key. Okay, so that is what normalization means. And in a few weeks, we'll actually talk about algorithms that you can use to normalize a set of relations. Because it's very easy when you create relations initially to have data redundancy in them. Okay, so there's a mathematical way to rigorously remove columns from relations or to move them to new relations so that you can eliminate this redundancy and normalize them. Okay, so that's pretty obvious. And when we get to the data definition language for MySQL, we'll talk further about different domain types and what you can do with them. Here is some terminology, and you'll hear me often interchangeably use these terms. So the formal mathematical terms for is a relation. The common vernacular that we use is table. When you're talking about the physical implementation, those people will often refer to it as a file. Okay, those typically are interchangeable terms. For a row, the formal name, mathematical name is tuple. The common vernacular that we use is row. And if you're talking about the physical implementation, you'll often talk about a row being a record in a file. Whoa. Okay. Is that okay for y'all? Okay. Third thing is we talk about the columns. The formal term is attribute. Oftentimes you'll hear the word property used also instead of column. And then when we're talking about the physical implementation, that's a field in the record. And you'll hear me go back and forth using these just because I deal with all three. And so it's just kind of whatever my brain at that moment is thinking about, it will come out as file or table or relation. Okay, so just for one moment, going back to 311 and the formal definition of a relation, basically a relation is a cross product of domains. So each attribute is associated with a domain, and a relation is a subset of tuples drawn from the cross product of those domains. So for example, if I have just two domains or two attributes where one attribute can take on the values 2 and 4, and the second attribute can take on the values 1, 3, and 5, then the possible set of tuples for that relation would be the cross product of D1 with D2. So for example, D2 and 1, or 2 and 3. Okay, so you have 6 possibilities. And a valid relation would be any proper subset, actually any subset, not just proper, any subset of these 6 tuples. Okay. And we don't do it, but just theoretically speaking, you could actually define a relation mathematically. So we might say that we want all tuples such that X is in domain 1, Y is in domain 2, and Y is equal to 1. So if we go back and we look at this set of 6 tuples, you can see there's exactly 2 tuples here, this one and this one, where Y is equal to 1. So so we would say in that case that our relation was these two tuples. Okay, or we could say that S is the set of tuples such that X is equal to 2 times Y. If we go back and look, the only tuple that satisfies that one is this one right here, where X is 2, Y is 1, so 2 times 1 is 2. There's no other tuple that satisfies that condition. Okay, now in practice, that's not how we choose the tuples in our relations. In practice, they're coming from actual entities like branch offices or staff, but I'm just, this is computer science. We're going to cover the theoretical basis. So I'm going back to the early 1980s and late 1970s when this was developed by a gentleman named Codd at IBM. And this is what he's thinking about as he's developing the relational model and paving the way for his future Turing Award. So this would be a relation with 3 domains. So the cross product there would give you this potential set of tuples from which to choose. And the most generalized version is that we have n attributes drawn from these n domains, and we take their Cartesian product, and that would give us the set of tuples from which we can choose. So any subset of those tuples would form a valid relation. Okay, questions about that? Okay, so much for that 311. Moving on. So we talk about a relation schema, and essentially a relation schema is like a class definition in a programming language. So in this case, it's a named relation with a set of attribute and domain name pairs. Think of a programming language, think of a class, think of like C++, you say class color, and you have, for example, maybe we have hue, saturation, and value. Okay, red, green, blue. Let's do the obvious one. You might have 3 properties, red, green, blue, defining it, and they would each be declared as an int. Okay, so that's a class definition, but that could just as easily be a relation schema. We have a relation named color, and it would have 3 attributes named red, green, and blue, and we would use integers as their type. Okay, and then a relational database schema is simply the collection of those relation schemas. So remember I said that a database has a catalog. That was from the last lecture. This relational database schema, that is the catalog. That is what the user can look at in order to figure out how to write queries on the database. Okay, so there's some rules associated with relations, and for the most part, they are pretty obvious rules. So relation names must be distinct. Okay, pretty clear because otherwise there would be ambiguity. But 2 is very important. So a cell, actually we did not give you a definition for a cell, but a cell is just like a cell and in an Excel spreadsheet. It is the intersection of a row and a column. So this 22-deer road would be a cell, just like in Excel, where cells are the intersection of a row and a column. So each cell of a relation contains exactly 1 value. So for example, if it's a phone field, it may not contain multiple phone numbers. It may contain only 1 phone number. This turns out to be one of the major limitations of the relational model and why people have investigated alternative models such as NoSQL, because the inability to store multiple values in a single cell turns out to be an enormous drawback in a lot of situations where you have semi-structured data. Now, there's ways to handle where a multi-valued attribute, and we will talk about them, but just suffice it to say that the relational model requires that attributes be single valued. And if it's a multi-valued attribute, we have to work around it. So this is one of the major restrictions. Okay, but it makes the mathematical operations a lot easier. And it makes storage a lot easier because when you lay out a record, you know exactly how much space often to allocate to a field. Okay, each attribute has a distinct name. That's pretty obvious. Here's another, though, fairly major restriction, which is the values of an attribute are all from the same domain. So those of you who do web programming may know that oftentimes you draw values from different domains. So for example, sometimes you have images, but if an image is missing, you just use a text label instead. So the domain could be either a text string or an image, but the relational model doesn't buy into that. They have to all be from the same domain. So again, that's where NoSQL gets its inspiration, is that oftentimes they want to have different domain types. Okay, each tuple is distinct. There are no duplicate tuples. So in a relation, remember I talked about the primary key. One primary key is always the set of all attributes in a relation, because a requirement of a relation is that each tuple be distinct. Okay, and if they're going to be identical, we can handle that. We just generate an artificial key. And finally, this may seem obvious, but for mathematicians, that is actually pretty important. The order of attributes has no significance. So mathematicians would say that a relation where, see if I can draw here. So a mathematician would say that if I had a relation, say staff, and I have first name, last name, and here's a second possible one, last name, first name. A mathematician would say that these two relations are different. But the relational model says no, these are the same relation. The order of the attributes has no significance. Okay. Not good. I may have just gotten, it may be that my PowerPoint is stuck. Ah, back. What's going on? Ah, all I had to do was click OK. Well, we'll see. Okay, there we go. Okay, next thing. The order of the tuples, just like the order of the attributes has no significance, the order of the tuples has no significance theoretically. But in practice, the order is very important. And we typically sort the relation on one or more attributes. For example, the last name. Or if this was a database of race times, for example, I used to be a runner, and you have race results, you might have it ordered by the finish time. So the order of the tuples in practice can lead to faster query response. If I'm looking for all people who finished the race in a time between 15 and 17 minutes, if all those people are clustered together in a file, then it will be much faster to retrieve those records than if it's an unordered file, in which case I'd have to search the entire file, right? So same thing, why we have things like binary search trees, so that we can efficiently implement range queries. But to a mathematician and for the relational model, theoretically, the order has no significance. Okay, so that was properties of the relations. What we move into next is keys. Okay, those things that uniquely identify a tuple. And the book uses slightly different terminology than we do. So stick with my terminology because it tends to be the one that is generally accepted. So a superkey is an attribute or set of attributes that uniquely identifies a tuple within a relation. So because every tuple in a relation must be unique, the set of all attributes in a relation is always a superkey for the relation. But as you well know, sometimes that you could choose a subset of that superkey, and that subset would still uniquely identify all the tuples in the relation. We refer to such minimal keys as candidate keys. So a candidate key is a superkey such that no proper subset is a superkey. So if we removed any attribute from the candidate key, it could no longer uniquely identify each tuple in the relation. So the two properties of a candidate key is that the values of K uniquely identify the tuple, and we cannot remove any attribute from that key and still maintain that uniqueness property. So we say that it is irreducible. Okay, so here with our branch and staff relation, all four attributes together are a superkey, but branch number is the candidate key because you can remove all three, these three, and you would still get a, you would still have unique identification. Now, we normally don't put a branch at the same exact location, right? So another candidate key is actually the street, city, and postcode, because we don't put them, we might have multiple, let's see, we might have multiple branches in the same city or in the same postcode. It's even possible that we have multiple branches at the same street address in different cities. I know that's unlikely, but it is possible. But if we combine these three attributes, pretty confident that we have a unique, that uniquely identifies it. So the street, city, and postcode would be another candidate key. Okay. Down here, you actually are in, believe it or not, a worse situation. Because flukishly, you could have a person with the same name in the same position with the same sex, born on the same date of birth with the same salary, working at the same branch number. Now, what's the chances of that happening? Infinitesimal, right? Probably less than your chances of hitting Powerball. But the problem is it's a chance. It's not zero. And for a set of attributes to be a candidate key, the chance that they uniquely identify tuples must be 100%, not 99.99999, 12 sigma stuff. Okay, it has to be 100%. So in fact, you cannot say that this if you remove the staff number, you cannot say that the remaining set of attributes with 100% certainty are going to be uniquely identifying each tuple in the relation. And therefore, we have to actually generate this artificial key. Now, in practice, you might say, okay, I understand I need an artificial key here, but why would I have an artificial key here? Why not just go with these three fields? And the reason is because of foreign keys. Okay, so if we didn't have this foreign key here, and we decided that street, city, and postcode would be the primary key, then the only way that we could represent a foreign key down in this relation would be to actually copy these three columns over and down here. So we generate artificial keys because they save space and prevent duplication of data. Okay, so where it's convenient and maybe one or two fields uniquely identify the tuples and they're fairly compact, we'll go with so-called natural keys. But when that is not possible, we often generate these artificial keys. Social Security number is an artificial key. Your student number is an artificial key. Your driver's license number is an artificial key. You have a lot of artificial keys in these worlds that identify you to different governmental organizations or private organizations. Okay. So in every, as you just saw, there can be multiple candidate keys. Okay. It is possible to have different candidate keys for the same relation. We choose one of these candidate keys to be the primary key. The other candidate keys become what we call alternate keys. Okay, so they still uniquely identify each tuple in the relation, but they are not the primary key. So in that branch relation, we chose the branch number to be the primary key, and the street address, city, and postcode then became an alternate key. Now, we also talk about foreign keys. These are a different animal. These don't uniquely identify a tuple in a relation. Instead, they point to typically a primary key in another relation. As I told you earlier, they are useful for joining two relations together. Okay, so a foreign key typically denotes a relationship with another relation. So the branch number attribute in the staff relation denotes that a staff member works or belongs to that branch. Okay, so relationships are a big thing in relational databases. On last Thursday, you may remember I said we will be talking about design at some point of databases, and we'll be talking about something called entity or ER diagrams, which stand for entity relationship diagrams. And what we're caring there about is the relationship between entities, things like staff work at a branch. Okay. So just to give you some practice, what I want you to do, so this is another schema that you are going to get a lot of experience with this semester. So it is a reservation system, and it has 4 relations: a hotel relation with the hotel number, the hotel name, the city where it's located. Then each hotel has some rooms and a type such as like a double or king size or suite, and a price per night that we charge. Then there is our set of guests. So there's a guest number, a name, and a guest address. And then there's something called booking, which contains a hotel number, a guest number, and when the guest is staying, and the room number. So this is like a reservation. Okay, so Brad is staying at the Holiday Inn from February 2nd to February 9th in room 303. So booking is, we could have called it reservation, but the book called it at the time a booking. So just so that you know, a booking actually happens to be, so a hotel, a room, and a guest, they're all physical entities. They have some physical substance to them. A booking is actually not an entity. It turns out that a booking is a relationship between, is a 3-way relationship between a hotel, a room, and a guest. A guest books a room at a hotel. So it's actually this booking relation is a second type of relation. The first type models entities, but a second type of relation models relationships. Now, what I'd like you to do is take about, I'm going to give you maybe 3 or 4 minutes, and I want you to figure out what are all the candidate keys for each of these 4 relations. Okay, so just think about that. Let me also, before, as you're doing this, a couple of things about those bookings. Guest is not allowed to double book. So a guest can't be in 2 different places at the same time or in 2 different rooms at the same time. And we are not like airlines. We don't double book our rooms. Okay, so to people won't be on the same room on the same date. So I'm just telling you that so that you can better figure out your keys. Okay, so here are the answers I would choose. And I know that I'm now going to make some assumptions. So hotel number is an artificial key. So it's going to be for sure a candidate key. Okay, it's going to uniquely identify each hotel. But in general, within each city, we are almost certainly going to give unique names to each of the hotels in that city. So in all likelihood, another candidate key would be hotel name and city. But because hotel name in particular is likely to be fairly verbose, like Holiday Inn Westtown Mall or Holiday Inn Downtown, we choose to create a more succinct artificial key as our primary key. But hotel name and city would probably be a fine candidate key. Now for room, it's going to be, whoops. Room number and hotel number is going to be our candidate key. So by itself, room number is unlikely to be unique because different hotels could have the same room number. And hotel by itself has multiple rooms. So hotel is not by itself going to uniquely identify a room. But the combination of a room number and a hotel number should uniquely identify each tuple in the room relation. Okay, unless we have a pretty strange sense of humor, why would we put two rooms with the same number in the same hotel? Okay, now type, we almost certainly have multiple rooms with the same type, whether they're singles or doubles or queen size or king size or suites. Almost certainly we will have, that's not going to give us any kind of uniqueness. Same thing with price. It's unlikely that price is going to give us any kind of uniqueness. If we try to take a room number and combine it with type or price, that's still probably not going to work because two different hotels could very easily have the same room with the same type or price. Okay, remember when we choose candidate keys, it has to be 100% guaranteed that it's unique, not like 99.99%. So really the only candidate key for room is room number and hotel number. For guest, sorry, I'm not getting, for guest is going to be either guest number or it's going to be guest name and guest address. Generally, we can do it in a way that we assure when we enter things that the guest name and guest address uniquely identify it. That if the operator types in a guest name and a guest address and it's a duplicate, the software would pop up some kind of warning message or error message and saying, this isn't unique, you need to make it unique. So you can have software, obviously, that guarantees uniqueness. Again, because the guest name and guest address together are fairly verbose, we generate a unique guest number. Now, booking is the one that I did it to make it interesting. In real life, what happens when you call up to confirm or cancel a reservation? What's the first thing the operator asks you for usually? My Zoom people can answer too.
Your last name?
Yeah, you're right, last name. But what would they be even happier if you provide it?
Room number?
Still looking. You're right, room number, but that's still not unique.
Reservation number?
Very good. Usually there'd be a reservation number. Usually you get like a confirmation number or reservation number. I deliberately didn't give you one. It would have made this one probably a little too easy. So in real life, the booking would almost certainly have an artificial key, which would be a reservation number or a confirmation number. But I wanted to give, this is the way it was actually also presented. So we took it like that. This one has multiple candidate keys. Okay, so in particular, where are we? You're wondering why I'm not getting a mouse cursor. So I am having to guess. Okay, so for booking, hotel number, date from, well, actually room number, and date from uniquely identifies a tuple because I guaranteed we don't double book. So any room, if we have the time that the reservation starts for that room, since we guarantee there's no double booking, it's unique. That's a candidate key. So it turns out it's so like to be able to get a cursor. I'm going to be given one. Okay, I'm just going to have to go to it's becoming such a problem that I am going to write it out in a separate slide. So okay. So another one is hotel number, room number, and date to. So we had date from, but because these things are unique and we can't have overlapping bookings, date to is just as good as date from, even though it's counterintuitive. Okay, but we can also look at it from the perspective of a guest. So we have a guest number and a date to, and that will suffice. I'm sorry, date from. And that gives us a unique reservation because we guaranteed that a guest could not double book on us. They couldn't be in two places at the same time. And because of that, guest number and date too also uniquely identifies a reservation. So in fact, this particular one has 4 candidate keys. The other one I'd already put down as date from. Has 4 candidate keys. You could choose any of them to be the primary key. Okay, probably you would choose guest number and date from because that is the most compact, and also a guest calling up is most likely to know their guest number. Now, as I said, more likely is that you would have a reservation number as a artificial key. But what I wanted to show here is that you have 4 separate candidate keys for the booking relation. So questions about that? Okay. Okay, so now we're going to transition. We talked about keys. We talked about super keys. Then candidate keys are super keys that are irreducible. Then a primary key is one of those candidate keys, and alternate keys are any candidate key that is not the primary key. And then foreign keys are pointers into other relations. So we had, but the keys we'll normally talk about in this course are primary keys and foreign keys. Those are the 2 that you'll most hear about all the time. Okay, so we're moving now from keys to 4 types of constraints that are placed on relational databases. So the first is something called the null value. Okay, it's not a null pointer, it's a little bit different. It represents an unknown value, one that has not yet been provided to the database and may never be provided. As an example, the property management database has a viewing relation where a customer, it says which property the customer viewed on what date, and there's a comment field. And the comment is optional. So if there is no comment, the null value is used to represent that. Okay, it is unknown, and as I say, may never be provided. So it represents, down here with C, it represents the absence of a value. It just means it's missing. Okay, and nulls come up all the time. So, for example, when you fill out applications, they'll say sometimes that your phone number is optional, your email address is optional, maybe your gender is optional. All of those then could be represented with null values if you don't provide that information. Okay, so null represents optional values. You have a large number of nulls. It often means that you might want to decompose that relation and split that field that is null off into another relation. But we'll talk about that later. It's not something to worry about now. So that's the first type of constraint, is null. Every cell has to have a value. So if that value is not provided, it is null. Okay, so you might think of this first one as stating instead that every cell must have a value. And if it does not, then it is represented with null. Okay, so that's another way of stating this first constraint. Every cell must have a value. Okay, the next two refer to keys. So in a base relation, which is a base relation is a relation that's physically stored somewhere in the file system. No attribute of a primary key can be null. That's called entity integrity. And it makes sense because primary keys uniquely identify a tuple. So if one part of the key is null, there's a good chance it's not uniquely identifying the tuple. So we don't allow any part of a primary key to have a null value. Referential integrity says that a foreign key either refers to an existing tuple in another relation, or all of its attributes are null. This is the referential integrity is the same as saying there are no dangling pointers. You might as well, so you want to write down something that helps you with referential integrity. It is, it's there are no dangling pointers in the database. Either the foreign key refers to a valid tuple in another relation, or all of its fields are null, one or the other. Okay, so that does lead to some interesting issues when you write the data definition language, because what happens if, for example, we delete a branch where some of our staff are working? What happens to those staff? Because we're not allowed to have dangling foreign keys. Okay, so there are different things that you can do on delete, and we'll get to them. But the people who design database or relational databases figured this out. They figured out, you know, on delete, what are the possibilities? It turns out you can cascade the delete, meaning you would then delete the the tuples with the foreign keys that depend on it. So if you close the branch, that means you fire all the staff. Or it means that you revert the foreign key to a default value, like headquarters. Or you simply put all nulls in there. So temporarily they are unassigned. Or you prevent the delete from happening. You say that if there's anything that depends on this key, it's like garbage collection, you can't garbage collect it yet. Okay, so that's referential integrity. And then the last one is general constraints. So these are often called business rules that are specified by the users or database administrators. So for example, we may say that no staff may have a salary that exceeds $100,000, or no staff member may manage more than 50 properties, or no owner may list more than 10 properties with us. Okay, so those would all fall under the rubric of general constraints. There are additional rules that we impose on the data that are arbitrary, but can be enforced with some kind of query. So all of these examples that I just gave you, there's ways to write queries that would check to verify that that the tuples in your database adhered to those constraints. So generally, data definition languages give you a way to specify these constraints. So questions about constraints. There's 4 types. Essentially, every cell has a value, and if it doesn't, it becomes null. 2, every primary key has all non-null fields. That's called entity integrity. 3, the third requirement is there are no dangling pointers with foreign keys. And 4, we can introduce general constraints that can be verified with queries. That brings us to the last topic for today, and that would be the ability to create views. So views are derived relations. There's base relations, and these are relations that are physically stored on the file system. Derived relations may or may not be. They may be cached for efficiency purpose, or they may be created on the fly, on demand, so to speak. And they are themselves relations that are created by queries. And you'll see sometimes they're called derived relations or virtual relations. So they are frequently cached because they're a relatively frequent query, and so you want to be able to quickly respond. So an example of a view would be a directory. That would be a join of the staff in the branch, because with a directory, you often want a person's name, their branch address, their city, and you want to be able to get that information fairly rapidly. So you might well store that information as a view called a directory, and you would actually cache it. And the reason you could cache it is because presumably that information rarely changes. People rarely move between branches. There's hopefully little turnover unless you're a really crummy employer. So you can cache it because you don't have to update it very often. If the underlying base relations are changing all the time, it makes no sense to cache, because then you're always updating the cached relation. So views are formed by a query on one or more relations, and they're dynamic, meaning that if changes are made to the underlying base relation, then the view has to be updated. So if a person moves to a new branch, we need to update our directory view. So it's important that we always, if we're caching our views and the base relation changes, then we have to make sure that we update the cached version. Now, if we generate these views on the fly, then that's not really an issue. We don't try to keep the view updated typically while you're viewing it. I suppose you could. Thinking about a shopping cart view in particular, that if there's some number of items, like, you know, how many tickets for this cruise are left, you might actually need to dynamically update that view, because if someone grabs the room before you do, you don't want it to be available anymore. So I guess even dynamic views, you may decide they have to be dynamically updated if the underlying base relations change. So why do we create views? I just told you one reason. If that query is frequently executed and the data doesn't change often behind that query, it may make sense to cache it so that you can quickly access it. Security, because it allows you to hide parts of the database from certain users, like the staff relation contains salary information, something you probably don't want to share with everyone. So you'd probably create a different views of that staff relation for different levels of management. The CEO and the top managers get to see the entire staff relation. Maybe a branch manager only gets to see staff at their branch. Maybe people at a branch get to see only people at their branch, but with the staff salary deleted. So views, what you can essentially do is for different groups of people, you can say, okay, this is a different view for each of you. Okay. permits users to access data in a customized way. So if you have a database for the property management, the salespeople want to view the owners and clients one way. They're prospective people to call up and try to get properties for. The accounting office sees it differently. They view it through leases. So the views that you present the accounting department may be different than the views you give to the sales staff. And they'll see different attributes for the same individuals. Okay, and then it can simply, you'll see this when you write your own queries, that it can often simplify complex operations because queries can get pretty complicated. So just like you sometimes use temporary variables where you cache, you do a computation, store the result in a temporary variable, then you do a computation on that temporary variable. Views essentially can be used like temporary variables to temporarily hold a value, and then you can do a further operation on it. Okay, so you just quickly talk about updating views. Remember I said if the base relation is updated, those updates should be immediately reflected in the view. That's easy. Okay, it's not very hard to see whether if you add a tuple to the base relation, you can check to see whether that new tuple meets the restrictions of the view query, and if it does, you add it to the view. If you delete a tuple from the base relation, you check to see whether it's in the view, and if it is, you delete it from the view. So it's not really hard to deal with updates to a base relation, but sometimes what you want to do is actually update the view and have the underlying base relations updated. And I can summarize this pretty much in with the saying, it's a bad idea. Okay, it's actually the number of view types that you can actually update is vanishingly small. So I can tell you right up front that most views are of one of two types. They are involved in aggregation, like it is, you ask for each staff member, how many properties do they manage? So it's what's called an aggregation operation where you are performing something like a summing operation. You're counting all the properties that each staff member manages. So that's one type of view. The second common type of view is a join, where two or more underlying base relations are joined together. The directory example I gave you, where you join a branch with staff. You can't update either of those two types of views. Okay, think about it. If you have an aggregation view that shows the number of properties that are managed by each staff member. So all it has is the staff member and the number of properties. Okay, so all we have is the staff number and the number of properties. That's the view. Okay, so I go and I say, okay, I'm going to change the number of properties that staff number 10 manages from 8 to 7. Okay, how do we update the underlying base relation? Do we just randomly choose one property and delete it from that staff member? That doesn't give us any guidance when we change the number from 8 to 7. Well, that's great. Which property are we supposed to delete? Or I increase the number from 8 to 9. Okay, that's great. Can you give me some information about that property? No, not in this view you can't. All you can do is increment the number by 1. So there's no way to update the underlying base relation. Hence, you can't update any view whose columns were formed from aggregation. Okay, same thing with turns out when you have a join, you typically are omitting certain information from the join, like that staff directory. You're not going to include like maybe the person's date of birth or their gender. So I go and I add a new person to the directory, but I can't update the underlying base relations because I also need to know their salary, their date of birth, their gender, all things that I'm not including in the directory view. So the directory view just doesn't have enough information to allow the updates to be made to the underlying base relations. Hence the second one, updates are not allowed when the view is created from multiple base relations. With these two strokes, we essentially eliminate any useful view that we may have created. Okay, but just for good measure, we'll throw in that if the query involves a single base relation and doesn't aggregate anything, it still better contain the candidate key of the base relation, which makes a lot of sense because if you don't have the candidate key, good luck figuring out which tuple you're supposed to be updating. Okay, so basically what this says is we're going to cripple your ability to update views. So don't even think about it. But on the quiz, I think there is a question about this. So for the quiz, make sure you know it. Okay, so with that, I shall let you go. And on Thursday, we get into the fun stuff, which is actually writing some SQL queries on a database. And I'm going to look into getting y'all databases set up, but I'm not sure if they'll be ready by Thursday or not. So we'll see. So I'll see you Thursday. Nothing is assigned yet, so enjoy your time doing homework in someone else's class. Okay, and I'll see you Thursday. And anyone have questions there in Zoom?
Actually, I got a question, Dr. Van der Sanden.
Yep.
The difference between, oh boy, I kind of zoomed past this.